All right, welcome to the part 2 for the magnetization of the nuclei and their relaxation and the transfer of the magnetic momentum. When you examine this compound, for example, nuclear magnetic spins are randomly distributed without external magnetic field. And when you apply the magnetic field, most of them are precessing in the alpha spin state. So they're tilted but precessing. Then identical homotopic hydrogens. So these three are homotopic. And those two are homotopic, but they're heterotopic, meaning they have different frequency, and also that's caused by different amount of electron density and the electric field around it. And the electric fields are not the only external electric field, but also the electric field caused by all kinds of electrons around. And after that magnetization period, the preparation period, we give a pulse, casually 90 degree, not 20, okay, just 2. When we give the pulse, it's basically we are turning on another magnetic field this way. So we are forcing these to flip. And depends on their frequency, we give a certain different amount of the duration of the pulse to make sure you get maximum value for the tilted X value, such as this. And as it precesses, average magnetic field is going right on the X. And also not only that, if you collect all the magnetized atoms field here and there, and you will have a maximum total magnetization that will be measured by the coil as a receiver. Then you turn off the pulse generator and then you wait. Have them to ready for relax back to the original stable alpha spin. There we had two mechanisms, if you recall, on the XY and the Z, right? Perpendicular 3 axes. This total magnetization can have two mechanisms. It can go this way or the other way. Depends on the frequency. They come around at different rate. Okay, T1. And then this can go upward. Together, it'll appear to have a spiral motion. Okay, but the change of the X value and that increases Y value as it go longitudinal relaxation mechanism, and that also has a certain lifetime, so period time 2. So in the combination of the two, what we measure here will come as a FID. So up and down sigmoidal motion is because it's turning around on the XY plane, and the decay in the intensity while it's going around is due to the motion of longitudinal relaxation. In doing this, you have neighbors, and their alpha beta spin gives different influence on their wavelength. I'm sorry, frequency. So that will be recorded here as mix of the sine cosine waves of the magnetic field during the decay. Then you will Fourier transform with a neighbor the signal for these three. It's a beta to the oxygen, so you're expecting it around the 2.0 ish, and you are expecting 3 lines there, and this should be around 2.0, right? 1.9 something, for example. And then the difference between these two or the other is caused by coupling with the neighboring hydrogens. Then I said that the strength of the coupling we call J3 because the coupling happening between this hydrogen and the alpha when there's no pi bond, then it's 1, 2, 3 bond separated. That's why it is J3. And that was mainly function of the angle according to the Karplus rule. As we measure the dihedral angle, right? In this case, this hydrogen has dihedral angle with this hydrogen about 180, but with this, between this and this, that's about 120. So the coupling will be different. However, they are constantly rotating around. Therefore, this fills the average of the two. Okay. However, if you have chiral center in the molecule, that creates unequal magnetic field for these hydrogen. So environment, that chiral environment causes asymmetric magnetic environment for these two. Therefore, they have a different magnetization, and that's why they suddenly becomes diestrotopic, which means diestro isomer-like hydrogen, meaning they have a different chemical, physical properties. And because of that, the neighbors will have a different coupling constant with these guys because they have a different frequency of rotation. Therefore, when I label this hydrogen as A, that as a B, and the C, A and the B are in the anti-relationship, right? Meaning they have a 180 degree and they have a quite big J value. This is pi over 2, 0 degree dihedral angle, and this is around 14. It could be a little plus minus variation, but say 14, and let's say it's about 12. And regular tetrahedral angle will give you roughly like 7-ish value. Therefore, coupling constant between A and the B, right? A and the B, 180 degree, is around 12 Hertz. And the coupling constant between A and the C, because the angle, they are Gauss interaction, so they're about 60, right? So about here. That say is about 5 Hertz. That's when either you lower the temperature, so you prohibit the rotation, or when you have a chiral center. In this case, it's not. Okay, please allow me to do that assumption without redrawing this example. Then what should happen is the hydrogen A signal is going to split into two, because the alpha and the beta state of spin for hydrogen B is influencing the frequency of the rotation for A in two different ways, right? When this is alpha and when that is beta spin. Therefore, you have two lines, and this gap is JAB, about 12 Hertz. Then you have each case, when this is A, that can be, when this is alpha, that can be alpha. And also there will be another case when this is beta, meaning this gives two different energy state for A, but each case you have again two different states when HC becomes alpha or the beta, and that difference is this much of coupling constant. It's a degree of the effect on the hydrogen with a certain angle between them. So 5 would be a little less than 12, right? So say this much, it's about same, so it should be about half, little less than half, so about this much I would assume. So split into two lines, something like that. For this case, say this was alpha and the alpha, for A and the B, alpha and the beta for A and the B. But now you have alpha beta for the C, alpha beta for the C for each cases, like I mentioned earlier. So you have 4 different energy states due to the 2 different neighbors. So your signal of NMR would be something like this. Doublet of doublet. The integration for each peak would be 1 to 1 to 1 to 1 ratio. Some similar case we can assume where these values are quite similar, right? Which means they become similar to that. If they're exactly the same, this is what happened though. Meaning these two are identical nearly. That's when we have a normal 2 homotopic neighbors. So same split, 1, 1, 1, 1. So this will have an intensity of twice. Then your peak would be typical triplet looking. What if this is a little smaller? Then you have a little split. So it must appear like this, right? And you can assume you may have situation, you have something like this as well. It's similar to this, but this case, the coupling constant happened to be small for the major split. Again, the smaller coupling has even smaller split, so it almost looked like one bunch, right? That could happen as well. So I feel like I have some pressure to show you connecting this phenomenon with the power of the NMR. I briefly mentioned in earlier video, but I'll show you a little more defined NMR changing due to the power of magnet of the NMR machine. Here I have ethyl benzene, and how many HNMR signals you expect. In the ethyl you have 2. There's no hydrogen here, but there are 5 on the ring. Then you can apply a symmetric mirror. Okay, then you can imagine having these 2 same, so 1 kind, 2nd kind, and 3rd kind, total 5 kind. And also the HA can have a long range coupling with the CH2 in the ethyl that's closer to the ring, but let's ignore that in this explanation. Also, I'm gonna ignore the long range coupling between A and the C to make the spectrum more understandable, so you can catch the concept that I'm trying to make a point here. You know, the NMR I used to use in my undergrad, 60 megahertz. Yep. I always see as an undergrad researcher something like this. Right. And you know, the regular benzene is about 7.4-ish. Then the integration is gonna tell me for the benzene ring 5 hydrogen if I calculate. Then later you got roughly 100 megahertz NMR. And they got a little better, you know, again around 7.4. You start to see a little thing here, and then the big peak has a little couple, you know, broad you know, split in the broad peak, and then a couple more wiggly, you know, something's happening there, but it doesn't help much. Our discussion on splitting pattern doesn't even apply there. Then later, way later, when I was you know, leaving my country, Korea, to come to US, Michigan, and do my master's, I had 300 there in Korea. Never touched it. Only the grad students were able to do some spectrometry measurement. And in Michigan, we had a teaching NMR for undergrad, 200 something, I forgot, 200 something to 300 megahertz NMR. And that gave some significant changes. It was something like this. There's some defined structure here and there, you know. As you can see, it's not one, couple signals are there, but we cannot tell them apart. Something like this. Yeah, we started to see something. If you really pay attention and measure out, that's what I used to do for my master's. You measure out these shoulder numbers and trying to imagine what type of you know, coupling constants are there, something like this, to match this. Then you can deduce how many coupling constants exist in this, and eventually we were able to get structure correctly. That was a very difficult but was fun as well. And 400, 500, you could get better pictures, and our job got easier. And during this time, we start to have two-dimensional NMR start to emerge, and the processing the data of the 2D NMR was quite a job. And that's the time when I was doing PhD. So 500, 600 megahertz or better, we start to see big difference. And the clarity of the 2D NMR also got very much significantly improved. we were able to get something like this. There you have a little shoulder here and there, you know, but we start to get clear peak. Almost for sure these are like one line. These are a couple lines, okay? And then what eventually we figured was like this. There are 4 lines, and you calculate the J value. They're all identical here. And then there we could see 2 spin system. You have these 2, and then those 3. And what happened, you can deduce, is if you think of the ortho, ignoring long range coupling, you have only one neighbor, so you expect doublet. Here you see 3 types, like 1, 2, 3 types of hydrogen, and you find 3 types on the ring as well. So the doublet should be these 2. So we know this is actually a split of our HA. Okay. Then this coupling constant is that of the A and the B. So your B should have that coupling constant in their splitting tree. Then you go to B, which is a meta. You have 2 different H's influencing this with the 2 different frequencies, and they're not same. Okay, they're similar. They're not exactly the same though. Similar, because the electron donating power of the ethyl is not significantly different compared to the regular hydrogen. So we would expect this split into, if you can imagine, right? 1 neighbor, 2, and then second neighbor, when their numbers are same, you expect a triplet. But if they're slightly different, then you expect something like this, right? 1 and the 2 and the 1. Then you wonder, right? You have ortho hydrogen coupled with a beta hydrogen, so that J value is right there, and the B. Yeah, and then you have para that has identical 2 hydrogens that should split into the triplet. That is not the case over here, and that's quite like a triplet. And assuming A and the C are not quite different, so they could be semi-triplet like we assumed, like this. However, then the reason that you cannot assign that as a B with a 2 similar coupling constant is because then C cannot explain this. Therefore, it's more logical to assign these triplet from your C that has a 2 identical coupling constant from the both neighboring B hydrogens. All right, so you have identical coupling constant here, that's between B and the C. So you have triplet anyway. All you have left is B, and you can see the pattern. How can you have this type of quartet-ish doublet of the doublet? That's when you have some difference between this coupling constant and that coupling constant right there, such as this and somewhat different, right? Something like that. So there you see two different coupling constants, and you can find out which neighboring atom, is it A or C, that makes this much of a coupling with the B, or that. And how do you do that? Well, there was a case you had a coupling already with the B. You had a A coupling with the B that gave this much of a coupling constant. So whichever one matches there, right, will be your coupling with the A for this B hydrogen. Say that was the case over here, making this much of a coupling constant with the A, then that J value should be equals to the JAB right there. Then this means this coupling constant must match with the JBC, and that should be the identical one in this peak for HC. So you measure the J value here, that should be identical to that. Okay. The way you get the calculation for J coupling constant in the Hertz, you need, I mean, it's useful to know, right? Because the X value is in the ppm. And when you read the signal location, the machine tells you some numbers and you get the difference of the two. Then whatever the ppm was, for example, the ppm difference was a 0.2, right? Then you simply multiply the strength of the magnet. Say your magnet was a 300 megahertz NMR, then you multiply 300 there. Then you come up with the 60 hertz. It's quite strong. It's too strong, actually, right? To be realistic, I should have said it's 0.02. Then the coupling constant would have been 6 hertz, more realistic number. But that's just to explain how to come up with the hertz from the ppm. As you can imagine, after looking at these type of realistic peaks, even that excluded secondary long-range coupling, the analysis of the splitting pattern is very useful information, right? It becomes very useful because eventually it tells you which hydrogen is next to what. However, some cases it's fairly difficult. Then later we came up with a 2D NMR technique. In this case, the technique like a COSY will make your analysis very easy. Even I think elementary school student can tell us which hydrogen is connected to which hydrogen without going through much analysis. That easy it became. Understanding how you run the spectrum and what's going on in the instrument as a grad student, that's tough, but reading the data become quite easier. Let's mention briefly how these one magnetization, say here in the hydrogen A, get transferred and influencing the energy state of the B there. As I said, nuclei is inside and very tiny, and you have an electron density around, and that's part of the sigma bond here, that electron, right? There you have an electron paired up Then you have more electron density, and they are orthogonal. When you hybridize them, they don't communicate. They're orthogonal. Then another orthogonal bonding electrons there. And you have the electron wrapping up the nuclei inside. And we know that it's not distance function. When you looked at the Karplus curve, you know that, right? So they are in the same, so you have a little influence of the distance here, advantage of the closeness, but it all has to do with how the orbitals are interacting. So you have first Fermi contact, the nuclei being up or down. That's causing some opposite magnetic momentum going on, and that magnetic field is influencing the energy level of one of the electron spin, different from the other electron spin. Okay, and then they influence each other due to the Pauli's principle. Then between the two, the orbitals are not communicating. So there must be some electrostatic interaction or magnetic interaction, not orbital overlap. So something like we can imagine there is London force. Then again, London interaction there. Then this electron spin here and here, they influence each other by Pauli's principle. And that influence, because that is creating certain magnetic field caused by the original magnetic magnetic field direction, that influences the energy level of the HB nuclei right there, because it has their own original magnetic field. That's what happened when we say alpha beta spin there is influencing the energy level of alpha and beta here through those mechanisms. So if you pick hydrogen like C, right, you have two hydrogens that are not same hydrogen. They're two hydrogen, they're not one hydrogen, right? But they are identical in terms of NMR, meaning their influence to this, they are magnetically equivalent. It's a very important concept. In this case, like this, those two neighboring HBs could be in the two same alpha spin states, or one beta, the other alpha spin state, and vice versa, then both in the beta states. And they have all different influences to C. So you can expect the 3 energy states for the C, and those 3 different energy states will have different frequency of HC, and the gap between them is the influence from the 2 neighboring B's on the frequency of the circulation during the relaxation process for HC. You know, that's gonna be like triplet signal that you are reading on the NMR, HNMR spectrum. And mathematically, you can come up with the formula for alpha spin and beta spin of the two neighboring group. And then you calculate those energy levels mathematically. Then you can kind of calculate the energy gap, and then you can calculate the coupling constant, or you can calculate the relaxation rate, like relaxation rate from that state to that state, or even there very low, but depends on situation, it could be improved, those things. So if you have same looking hydrogens with the two methyl groups, those two hydrogens are called homotopic protons. So each hydrogen must have same coupling constant with the neighbors. When it does, the other one does the same way with the same J value, because they are homotopic, they are identical in all kinds of ways. So not only the distance from the electronegative group, if you have any, but also in terms of a magnetic field on this side above the page or below the page, magnetically they're also identical. So how do you find that out? You can imagine replacing the hydrogen with other thing, X group. And compared to the case you replace this H with the X, then if you draw out the two isomers, you can see they are identical. They're literally identical. You can overlap them. They're superimposable. Try that out. That's how we know they are homotopic. There are cases where you have molecule like this, right? This carbon is not chiral. Thus, people would think these two hydrogens should have the same chemical shift and the same property. Well, let's see, right? And again, if you substitute these hydrogens with the X group, that's different from everything else, and you do the same thing with this, when you compare those two isomers, they're not superimposable, but hydrogens are in the enantiomer relationship. So we call enantiotopic hydrogens. Then, as you know, enantiotopic hydrogens are identical unless they are interacting with another stereoisomers. The surfaces that are stereoisomers, chiral surface, or they are interacting with the enzymes and proteins, or they are in the certain chiral environment. You can have a Lewis acid that is a chiral, and that chiral Lewis acid can interact with the oxygen. Then suddenly these two turn into not so mirror image of each other. They're not enantiotopic anymore. That is actually the case. Say I have compound that looks similar, methyl, methyl, methylene, methylene, but if you have methylene, but there you have finally some chiral center, then the magnetic field you get from this chiral area for this hydrogen and that hydrogen, they're not identical. If you use the substitution method, put it there and put X group over there, you draw two isomer, you'll see they are diastereomer relationship. So these are in the diastereotopic hydrogen. So they must have different chemical shift. Okay, so due to this three neighbors, they split. Also, they each other are not family anymore. They're different, so they influence them with a different spin frequency. So they change their spin energy level in addition to the three identical one affecting them. So these will be appearing on different chemical shift by not much, but somewhat different. As you can see, the phenol, the benzene ring creates strong local magnetic field. So this will be influenced much more than this. So somewhat different chemical shift. I mean, alpha to the oxygen, so they're all near 3 point something, right? Then you first split by the geminal hydrogen, big splitting. Then each line split by 3 hydrogens, so quartet. I mean, I'm just assuming like this. Very complicated. You can see here 1 to 1 to 1 to 2 to 1 to 2 to 1 to 1 to 2, because there are 2 and 2 2 coming together, right? In my imaginary coupling constant, it'll change when you have a real value, but either way you can imagine the intensity and the number of splitting you get, and they are merged. So not easy to read out, but when you see these complex splittings going on, something like this, you know, you have diisotropy hydrogen, because integration will say just the 2H, and then so many not symmetrical signals, so they're not simple triplet, quartet, quintet, or you know, whatever. So you have to assume there must be some diisotropy hydrogen. And additionally, there are somewhat more different situation. Obviously, these appears around sp3 carbon hydrogen area, although the bond is more having more s character, so the hydrogens are more de-shielded than usual sp3, and they're next to the double bond, so it feels the shieldedness of the anisotropic effect of the double bond, and so on. And these are on the double bond, so you can also think of it as around 4 to 6 area. So two different system, right? It's our custom, like putting the one near the 0 A, the one away from it, as X. So we can say these two are actually identical, even magnetically identical. When you think about it, this to this and this exactly same, and compared to this towards this and this, magnetically you are getting affected by these neighboring groups, and the functional groups identical. So these are magnetically equivalent. They are magnetically equivalent, so they must get the same chemical shift and the same coupling constant by the neighbors. Okay. And the case like this, let's say you have hydrogen there, HA, HA. Then I put the H, say X with the electronegative group, and here HX, and chlorine there. All right. And if you rotate around this symmetry axis, you can actually interchange HX and the X, A and the A. So they are symmetrical by rotation. By the mirror, they're not. Okay. So you want to give the same chemical shift for this and this. You cannot do that because the distance of this hydrogen to that HX and that HX prime, right? That's not same as distance from here to there. You know, compared to this to that, it's not same as this to that. So this, whatever the frequency of nuclei this may have, the influence to this is different from influence to that. It's different from here, right? The influence of this H to this and this, they're identical. So that makes them feeling different influence of the neighboring group, so they are not identical. They're magnetically not identical. Therefore, they have a chance to have slightly different chemical shift like this, and then their coupling constant to this and that will be different from this and that to this guy. So magnetically inequivalent. When you have more complex structures like this, for example, it's not that complex, but let's, comparing to other regular organic compound you are dealing with, you can say this is somewhat complex. So this and this, they're not identical, obviously. You can say this is in the same, the carbon is in the same distance from the double bond. So the two guys on the same carbon should have the same de-shieldedness. True. But you know, the de-shieldedness caused by inductive effect is not only thing that determines how much magnetic field is reaching inside of the nuclei. There was a magnetic, local magnetic forces, including anisotropic effect. So you can say, yeah, these are de-shielded, they are on the sp2, but also, you know, when you are in the magnetic, external magnetic field, the electrons moving around this way and creating the perpendicular magnetic field influencing this way, and you can see they are, the local magnetic field is adding up to the B0. So these nuclei are feeling more magnetic field, so energy gap increases, so you need a higher ppm to observe them on the NMR, right? And their rotation is quite fast. And when you look at them, they don't feel any of them, but especially this don't feel much. However, this one is far away compared to this, right? But if you have any influence by that, you can predict the magnetic field that is actually coming down to the double bond to make the magnetic field in a circle in completion. That area, the local magnetic field is going against external one, so you are losing. It's like you are getting shield because you are canceling the magnetic field. So net effect to the nuclei here is you feel less magnetic field, external one, so your alpha beta spin frequency will be also lower, okay, even compared to that. So that is most closest to the 0. That's why it's labeled as A. That's M in the middle. That's one of the most de-shielded one in the molecule. So you have the two magnetically identical. Distance from here to there, identical. For this guy, you have an identical 2 group. You cannot split by regular J3 coupling, but through space they can interact. Again, I cannot stop mentioning, but like 2D NMR, nosy, that detects the interaction through space, ignoring through bonds. It can tell you where this is located and headed to, pointing to, and so on, right? So shielded one, de-shielded one, not influenced one, so it comes around same number, right? 0.9 or 1 ppm ish. This will be the room temperature NMR of the hexane with a decent NMR. And first, you notice you don't see good splittings, and I want to take your attention to this triplet. We understand there are 6 hydrogens that should have a triplet because of the 2 neighbors. Then you can see it's not really clean triplet. You frequently notice that they're not really clean triplet, meaning those are exactly identical. They're magnetically not really identical, and you should know that in the room temperature, this molecule do not exist always in this most stable anti conformation. It could be in the equilibrium with the other conformers. It doesn't have to be very unstable eclipsed. So let's make it gauche. And every single bond here can make a free rotation. And also in every single conformation, say this hydrogen's relationship to other 2 neighboring ones, for example here, right, this one to other 2, they're not identical. The angle changes. Therefore, the magnetic environment is changed. Therefore, the chemical shift and coupling constant will all change. They're quite similar, not identical. And this NMR will show all those signals from majority of that, and then minor of that, and minor of other conformations value together. So ideally, if you slow down the process by lowering temperature, that's one of the main tools, but there are other methods. But anyway, if you slow down the equilibrium, then you'll start to see these peaks here, or even these clumps of peaks shows more clearly separated individual signals of each. Therefore, even those 3 identical, we always hypothesize them as identical, but those hydrogens having different values of chemical shift, different values of coupling constants. That is the reality. So even these 2 homotopic hydrogens, and indeed you guys think these 4 are same, and those 4 are another same type of hydrogens and you expect 3 types of signals. That's true in the limited situation, right? And we are saying those homotopic hydrogens are not coupling, but that's not always true. Like I said, if you lower temperature, this will couple with that, and that will couple with these guys. Then the coupling constant between this and this will be different from that and that. So you don't expect the line split it into 3 by these 2 neighbors. I mean, you have more neighbors, and they are not necessarily identical anymore. It depends on their conformation. In conclusion, you actually have a coupling going on between these 2 as well. However, in this open system, it's freely rotating and so on. In average, they have same environment, thus same frequencies. Therefore, even when they couple, their frequency do not change. Their energy level stays the same. But if you start changing things around, then they do not have the same magnetic environment. Therefore, the coupling is making each other some changes. Depends on their spin state. Therefore, the alpha beta state of this will make changes for this guy. When you create the situation and environment that's not anymore identical for them. Let's ignore all other couplings just for convenience of making my point again. Say you have these 2, and we can calculate their energy level. Thus, we can calculate the angular momentum, angular frequency of each nuclei. Then the first energy diagram you can get out of the calculation. You can use your classical or modern spin movement to justify it as well. So you have, say, identical magnetic environment for them. Then the nuclei inside feel the same magnetic momentum, and they don't influence each other. They're 2 same thing moving, so their frequency do not change. Okay, so making first hydrogen change the spin while the second one keep the spin takes a certain energy. That amount of energy is equals to the other case, keeping alpha spin same for the first guy, and the second guy change the energy level. The energy difference is the same. The amount of energy it takes is the same, because this spin is not touched, right? It's only determined by the external magnetic field. You feel same amount of external magnetic field for both of them, so the energy gap is the same. Therefore, the frequency of the 2 different hydrogen must be same. So let's just say you fix the second hydrogen's spin, right? And you have excitation going on for the other one. Or you fix the second one's spin from spin for a beta spin state, and you again promote the first one from alpha to beta, either case, the energy gap is the same. So when they relax down in the Marden spin motion, right, comes back down to the original net magnetization, the relaxation period will be identical whether the neighbor is alpha or beta. So you have only one frequency. If you switch the role for second atom, if you fix the first one, you get the same energy gap, so the neighbor's getting only one frequency. And that, compared to these, happen to be, as we said before, identical. So you have one hydrogen giving a certain frequency, and the other one give exactly same frequency. So the integration's twice, but your frequency, relaxation frequency, will be same. That's why after they interact, you come up with the 3 different energy level together as a 2, but the relaxation of each particular hydrogen will be same. You just have more intense frequency, more intense signal of the same frequency detected as FID. But when the magnetic environment for these two are not identical, then you can imagine when first one being alpha, second one being beta, it's not necessarily same energy as the first one being beta and the second one being alpha, right? It's easy to conclude. So if you assume same thing that we did over here, when first hydrogen get excited, you have actually 2 different energy gaps. So when you observe FID, the relaxation has 2 different frequencies. So for first hydrogen, the relaxation coming into 2 frequencies. Same for the second one. Therefore, you get 2 lines for one signal for one hydrogen, and the other hydrogen has a different environment of magnetic field. So the chemical shift, the energy gap of alpha beta is different, right? So it must have a different chemical shift, and again 2 different relaxational half-time. So you get 2 sets of doublet, one for first hydrogen, the other doublet for second hydrogen. So this is how the spins, they interact and transfer their energy during the relaxation after the pulse given change their spin state. All right, let's examine this case before we jump to the 2D NMR briefly and stop for this video. And it will take a while, but I'll come back with a more 2D NMR spectrum. Our students, even for majors, unless you do research in organic lab, you wouldn't need this as much. So I'll just wrap up here with a simple cozy 2D NMR, and then I'll probably go to the UV spec and make more video later about 2D NMRs of different kind. I promise. So the chemical shift of hydrogen for CH2 was 1.2, and detaching hydrogen gives about 0.3 more. And having chlorine, you add another 2.3-ish. So let's just say overall for this alpha hydrogen, around 3.5 or 6. Okay. Then all of these around 1.2-ish. So let's just say 1.3, 1.2. And then hydrogens, having hydrogen there, I should have considered this hydrogen being beta to the carbon. You know, you can say this is about 1.5-ish. Let's just say 1.5. Yes, I'm in a rush to wrap up this video because it's quite lengthy already. Anyway, so having one more hydrogen, deduct 0.3, so 0.9. And this one close to the chlorine, but you have one more, so let's just say it's about 1.4 or something. Okay, then if you draw them out here, considering the typical normal situation of splitting pattern of J3, this one having 2 hydrogen, you know, the average energy you feel by these two will be, when it's alpha, 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 beta, 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 3 different energy level. All right, so it goes to the triplet and so on. When you deal with this hydrogen, for example, you have 2 different neighbors and they're not exactly the same, but let's just say you have the case, the J coupling constant for these hydrogens, and these hydrogens are about the same. Same for this guy. Those gives about same splitting for that, and so on. Okay. So let's create some NMR spectrum based on those. Something like that, without the slight difference of the coupling constant for the neighboring 2 different groups. I came up with that, right? So they're 3.6 with the 5 neighbors. So we're expecting roughly 6 lines. 1, 2, 3, 4, 5, 6 lines, right? And the coupling constant for splitting of this and this should be about same as this, as we spoke about earlier. In reality, if you see a little more defined lines, then you have to calculate carefully for 2 different coupling constant here and here. That gives you idea, okay, which one's next to which one. Anyway, so then next more shielded one, I mean de-shielded one, are these 2. Then you know, here you have the 3 hydrogen being doublet, which is this guy, and this one has 3 and 1 more. So 4 lines you expect, and you see 3. I intentionally drew it this way. This happens really frequently. So what happens is you have a 1, 2, 3 and expecting something smaller here, but happen to be add up to this. So you have to imagine something imaginary here and became part of it. Okay. So you found these 2 beta carbons. Then you have a 1.2, which is this one, and having 5 neighbors. So you're supposed to have 6 lines, but I only gave you 4 lines. And that's when you have to zoom in and see. You can zoom in if you operate NMR. Zoom in this area and you come up with a more fine structure of NMR, and you may find these little ones. Okay, so that gives you idea. When you count the lines, you don't really always just trust what you see. Then there you have a triplet for 3 hydrogens right there with the 2 neighbors. But like I said, it may not be clean triplet, and it might not be clean sectet or something. Here I will switch to the NMR with this example, because although we were decently figure out which signal belongs to what, depends on their chemical shift and their coupling constant, but you know, the two signals like these, they're not that easy sometimes. If this was a case, you have doublet versus quartet, and you're able to tell. But even these two are not that different in chemical shift. So, you know, I'm sorry, these two. Therefore, also they are both multiplets and not easy to tell which line is which. And this compound has only 6 carbon. I just want to say there are, you know, normally more carbons in your sample, and you will have a multiple of these cases. So it's not always as easy. But then you run 2D NMR like this. Here you can see that hydrogen NMR, one-dimensional, the other hydrogen NMR, one-dimensional. Plot this way, you create a space, two-dimensional space, and that is the 2D NMR. The plot method is two-dimensional, but we also are using 2 spin systems mixing, and that's the reason also why we call this as a two-dimensional NMR, because it has a 2 different independent variables mixing up and creating new information. Okay, so for 1D NMR, what we did was you put the sample and magnetize them, and then you give a certain pulse. All right, so for individual hydrogen, they need different duration of pulse to have them line up on the x-axis. That's where you measure the intensity of the magnetization of that particular hydrogen. Okay, we do that. So now your spins are on x. Then you start to, I mean, you can give a little waiting period, or you can right away start measuring FID, and then Fourier transform to get signal. Okay, that's how we did for individual hydrogen. Then when you run 2D NMR like this to correlate, say this hydrogen, is it, which is this guy, is it correlate to this or others? Okay. Say, you know, this will be useful when this is more complex. I'm just bothered by the fact that these are clear with the chemical shift and splitting pattern in this case. For 2D NMR, typically, yeah, we magnetize them, give first pulse, have the net magnetization on the z-axis, you know, flip to the x. So you wait a certain period of time, delay time. That's when this one goes to panning out. It has a, you know, period of T1. Depends on the experiment, you give half of that time or quarter of the time, and so on. Depends on what you want to extract, what type of interaction with the neighbors you want to allow. That period of time sometimes is referred to evolution. So in this panning out relaxation process, how quickly it is going in the alpha direction or beta direction is affected by the neighbors, like this, for example. With the two different neighbors, you get 3 different influences. So you are making a bunch of different frequency, some of them here, other ones are there, and different frequencies going around. So we let them evolve, okay? Let them get influenced by the neighbors, and let's have them different frequencies. Then you give second pulse. You can give 45 degree, 90 degree, and see which one works out better for you. But you give second pulse, and say you gave 90 degree. Then let's pick one of the influenced spin, magnetic spin that's there, okay? Then this one has, X component of vector, Y component of the vector. You give second pulse, say it was a 90 degree, then what happens is, you see, you give a pulse here, for example, the magnetic pulse there, then the spin will turn into, this. So far, what it means is, like, when we are intending to detect the correlation of neighboring group, see which one's neighbor of this hydrogen in the spectrum, we are setting the receiver for this frequency, okay? And then based on that, we give 90 degree pulse, and then we let them delay and mix different amount of time to mix with the different frequency hydrogens, and some of them are not mixing, so it wouldn't make any difference, right? And say when you give this much of a waiting period and then give next pulse, then you are getting some vectors that is made up by the influence of this hydrogen. So you get a very intense relationship between them, obviously. So diagonal peak you have, but you'll see a little bit of changes in the relaxation, because we are measuring these components, Z components and the X components. But when you are waiting different amount of time, then for this frequency and that frequency and so on, you don't expect any changes. Okay. Also, when you are now exciting this hydrogen, and you are let them mix and determine a certain time t1 here, duration 1 there, then you're expecting some changes. And obviously between these two you expect a big circle. So when you analyze this, you know you are actually connecting these two diagonal peaks according to those two cross peaks. Meaning these two are related. Meaning if you look at the 3.61, which is this one with a strong diagonal peak, right? That's related to these two. So I didn't even mention this one, say it was there, and they're overlapping. This and that must have cross peak right here, as well as right there. Here I had to redraw the spectrum with a labeling and color coded to save time. And let's track down the backbone. Here CH getting connected to two different hydrogen next door, like two different hydrogens, and one is this multiplet and the other here this CH3 beta to the Cl. So it turned out that this we originally labeled as this CH3 beta to the Cl. This is the CH2 beta to the Cl. But we know that this CH2 hydrogen has a coupling with the CH alpha to the Cl, but also has another coupling with this, and that is the CH2 next to the CH3, which is this, right? CH3, CH2. And that's neighboring to this CH2, the beta to the chlorine one. Yeah, so we can keep track of that. So this neighbors to this. But also, I'm sorry, this guy, right? Neighbors to this, and that's neighbors to this CH2, and that is neighbors to the methyl group. Okay, so in order to observe the cross peak, you have to choose a certain peak and give the pulse to have them there, and then have them evolve, right? Influenced by the neighbor, and you give the second pulse. Then you measure the magnetization there, and that's gonna also span out, right? Because it's still in the magnetic field, external one, and then you removed some of the elements to the z-axis. So this time this will be solely influenced by the neighbor group more than before, if there was any. So that T1 mechanism we are measuring here. So that's when mixing is happening. So let's say that's a T, when we are going through the T1 mechanism, but we are measuring the FID. And there during the mixing, we are waiting different time to allow the mixing to see mixings happening with this frequency neighbor, this frequency neighbor, that frequency neighbor. If there's any difference, then you get some signal And if there's no difference, meaning there's no influence of these guys on the relaxation process. There's a 2D NMR called an OZ that is actually using this Z value. Okay, so you give another pulse after the 2. And you are making this Z to go to X. I mean, this goes to the, now, you know, this flip 90 degree goes to the X. Then we detect how it how this go back to the Z. And there we measure T2 time. Okay. So that longitudinal mechanism we are trying to measure, that is the mechanism by the dipole through space, different from the neighboring group's mechanism. So this way you are able to extract the information about through space. As you can see, this disaccharide molecule is quite complex, and you can imagine peptides, and the amino acids are separated by amide bond, where these saccharides are separated by oxygen. So we say this structure here, all of these hydrogens are in one spin system, and they're not going to couple normal way, so it's another spin system. So you can keep track of these things using traditional just hydrogen NMR, right? But they're quite now similar. So when you have a little difference, for example, here you have another methyl group or something by some reason for your synthetic tool method or whatever. It's awfully similar, but they're not symmetrical. Then keeping track of these with a regular NMR will be almost impossible. Then you will have to find the signal for the carbon here. That's probably the easiest thing to notice on the NMR. Then you can run so-called homonuclear 2D NMR. So you are doing hydrogen coupling with the other hydrogen, but here you don't have any neighboring hydrogen. OH hydrogens are not coupling, right? Because they're fast moving. Then you have to go for 2D NMR, all right? But normal 2D NMR, like a cozy homonuclear 2D NMR, cozy, you can see the coupling between these two types better. Then this hydrogen is next to the oxygen, so you can see them clearly. Then this you can see on the cozy connected to something, and that something must be this. And then that guy coupled to something, that must be this, and you can follow using J3 coupling in this case, right? Cozy. But eventually you come to the point like here, and then you cannot see which one of these hydrogen carbon is connected to that. Then you have to see these connecting. So that requires connection through space. That's what I mentioned earlier, NOZ or ROSY. There's thing called HOSY, HOSY, and so on. Then there is a heteronuclear NMR, like carbon-13 is usually coupled, right? So when you run carbon-13 with a pulse, you get the FID of the carbon, but you use a frequency of the hydrogen because they have a different frequency due to their nucleus having different mass and charge. You can have decoupler on for the hydrogen frequency, meaning the hydrogen atom, all frequency of hydrogens, they will get excited and saturated, and that can have only one spin state. So carbon would not feel different number of situations. Okay, although there is a little bit of a noisy NOE effect, not noisy, I'm sorry, NOE effect through space. Sorry, the carbon and hydrogen, you know, what's on the carbon, how many hydrogens you have, 1, 2, 3, right? And when you saturate them, because the relaxation from the saturated hydrogen coming down have influence on the relaxation of the carbon, there is a little enhancement of the carbon. That's why we were having in your DEPT spectrum, if you remember, you have a positive influence of the intensity of carbon-13 or negative intensity, and so on. And even regular carbon-13 NMR, some signals are taller than the other, and that has to do with the NOE effect. That coupling is obviously J1. It's one bond coupling, right? So there are heteronuclear NMRs, such as a Hetker or inadequate. So unlike the COSY, you are relating carbon-13 with the proton NMR, and you are doing acquisition of the carbon-13, so you are setting your detector for each carbon type. Then you are changing your mixing period, evolution period at different time to mix with this hydrogen, this hydrogen, this hydrogen, to see any changes happening on the relaxation process of the carbon through the transfer of the magnetization from hydrogen to the carbon. If you see any, you will notice some signal. This case, there isn't going to be any cross peak, diagonal peak, because they're not identical spectrum, right? So 2D is 1 plus 1 D NMR, and you are correlating different atoms. Okay, that way you can see after labeling all the hydrogens corresponding to all the hydrogens in the structure, you need to know which signal on the NMR, carbon-13 NMR, correspond to which carbon. And by running these heteronuclear NMR, you can exactly label which peaks corresponding to which, relying on the information on the hydrogen, or vice versa, whichever is a more easier route for you. If it's more easier for you, you can have an acquisition for, you know, hydrogen while you are playing with the carbon. Okay, for the same type of information, they're slightly different, but you can get the similar type of information from HSQC or HMQC or HMBC, right? Those gives you like J1 information, like this carbon and this hydrogen, or this carbon and this hydrogen, because you know which one's connected where. You can label which carbons connected to which, or vice versa, and you can get acquisition if relatively carbons easier, then you go like Hetker, If hydrogen acquisition is easier, then you go for HMQC, HMBC, stuff like that. And in case of HMBC, you're not only doing this, right? You can go, I mean, that's actually for HMBC, you can go more bonding. You know, J2, J3, J4, you can correlate this to that as well with a multiple pulse and playing around the spins. Then there came HN adequate. Just like the HMBC, you can correlate far away atoms. Then nowadays you can correlate 2D NMRs, right, with another 2D NMR. So one 2D NMR, right, say it was a hacker, and then you can have another hacker, or you can have a cozy, correlate them, finding your signal in this box, three-dimensional box. Then you can correlate more in detail. These are for the normally we do nosy, correlate with others, and somewhat different property to the NMR each other to you know, elucidating the big structures like proteins and, you know, big biomolecules. There are a lot more I want to cover, not only just introducing 2D NMR for the major, such as you know, solvent make big difference in NMR. The chemical shift and splitting pattern and everything change. Therefore, the looking, the appearance of the NMR of the same compound in different solvent look sometimes quite different. Also, when you run the NMR as a neat sample or different concentration sample, also that changes the NMR appearance different, so the interpretation sometimes difficult. So you might want to switch solvent or concentration. Not only that, we have lots of tools to make a certain particular signal shift away from the cluster. So we can add some of the heavy metal ions into the NMR tube, so you can separate out a certain you know, complex cluster to make the NMR simpler and more readable. And yeah, a lot of techniques are there, but for now I'm gonna hold on the series of the NMR, and explaining NMR without more detail example becomes somewhat not so interesting to me. So I'll come back with the first UV spectroscopy, then probably finish up the organic synthesis. Then I'll deal with a more practical and deeper instrumental or technical theoretical stuff. So until then, please don't give up. See you later.